Welcome to 7.3, applying statistics, samples and populations. So I hope your quiz went well, 7172. What we're going to do now is kind of start applying this stuff to the real world. What statistics is in general is kind of the idea that we can take surveys and ask questions to a lot of people, but we want to make blanket statements about everybody, okay? Take the classic example of commercials. You see people on commercials make statements all the time that everybody wants this product. I don't know. Take, for example, Amazon Echo, right? The new Amazon nonsense that's come out with the voice and then whatnot. Did they actually ask everybody in the world whether they liked the Amazon Echo before saying in their reviews that people like the Amazon Echo? No, probably not. They probably asked a lot of people and decided whether that was enough people to actually say that people liked it. Okay, you see the same thing with drug tests. They're not going to test the drug on absolutely everyone in existence because, let's be honest, nobody would say yes to that. But they ask for a certain number of people. They get as many as they can to do a test, and they see, okay, did it work in a lot of people? Okay, then we're going to say it's probably going to work for everybody. So we get this big kind of dynamic of where statistics kind of feeds into the probability of it working on everybody. You can kind of view that idea as the difference between sample and population. So what we've been working with is actually population parameters. Parameters are those things that we have been finding, the mean, the standard deviation, right? Or sorry, we've been given, and then we would calculate stuff based off that. That has already been decided that works for everyone, right? That for the whole population of everyone at that high school, this is true. For the whole population of that test, this is true. I know it sounds weird to call a test a population, but it's true. Everything's been decided. Nothing is being like questioned as to whether it's true or not. So therefore we use mean, mu, and sigma. These are the ones that we've kind of been working with, right? So those are our parameters for those bad boy. The parameters are the things that statistics is actually trying to find. When the drug is, you're trying to say, does the drug work? What is the average amount of time that the drug works in the system, right? Is that enough? Is that what we're saying? So that's what we're actually saying. When it's on the label, it says will work. You can't take another one for 6 hours. That's because the average lifespan of this drug is 6 hours, right? That's for all the drugs. You're not saying that was just the average for that one sample. On the flip side, you have sample. Sample has the same ideas, but we don't call them parameters because they're not really guesses. They're not estimates. They're not, well, we think it's this. They're actually known. They are calculated numbers. They are the numbers that you add up all the numbers and divide by how many you have. That's the mean. And so we're going to use a different symbol for that. We're going to use X bar. And for standard deviation, we're going to use S. Those are the ones that have actually been calculated. Those come out of your sample. When they take 512 people and do a study on them, that's their sample. Okay, so this is the actual, and this is the guess. Now let's be honest, that's a pretty good guess. If you're going to test something on 512 different people and get data on that, you can pretty much guess whether that's going to be right or not, right? Whether this drug is going to work, whether this drug actually has an average lifespan of 6 hours. Or whether people actually like the Amazon Dot. Now, 512 to liking the Amazon Echo, is that enough, right? Like, is 512 people in the United States enough to really claim that everybody in the United States likes it? Probably not. So sample size is also really important. The sample size, you want to make it as big as possible. You want to try and get as close to everybody as you can. That's why they often pay people, because they can get more people, right? So you can't really make statements about a couple people. Take, for example, a test, right? Statistics on a test is usually something you guys have to deal with. If they only looked at 2 people's score in a class of 42, and they decided the subject on that, or so decided the average on that, and the standard deviation on that, it's not going to be accurate, right? Because there's only 2 people out of the 42 that are actually in that class. That's not good. If they took maybe 40 out of the 42, they're probably pretty good. It'd be best if they could take all 42, which is when you get your sample actually matching your population, which is really ideal, and it's super awesome if it does. But, most real-world applications, you can't do that. But this point still stands. The more you can get towards the population, the actual number of people, the more accurate it is. Okay. We're going to hit on this again in in 7.6 when we talk about confidence intervals and how confident we are that these are true. But let's talk a little bit more about how to find these sample statistics before we go claiming that they are accurate. Okay, so here's what we're going to do. First off, I want you to go to the next page, go on page 11, and I want you to put a big old star by this. Okay, this we will talk about in a moment, but you should have gotten already today a TI-89 calculator from me. Please, 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 please return it, because they are $80 a pop if you don't. They are $80 that you will be charged for if you do not return this. And no, you cannot take it home. So if you have one, that's awesome. Because they're so expensive, I'm not going to require you to buy one. That would be cruel. Okay, so you do not need to buy one. You're only going to use it for this part of the class, and then if you go on to stats, you're going to want to invest in one. However, option number 2, Desmos. Desmos, as many of you know, is a good online calculator. It has a statistics version. It has all the statistics stuff there. It has tutorial videos. It's fabulous, and that one's free. So if you could use that one online at home, that'd be great. In class, any test you take, any homework you do in class, any notes you take in class, you can use one of our calculators. But if you did invest in one because you know you're going to go on, I'm not going to ask that you have to, just, if you wanted one, they're pretty pricey. So here is how we're going to enter. If anything we do in the notes is right here, these are the two biggest things. The only thing on there that's maybe not, or the only thing not on there is how to clear your data, but I have a video on that as well. There's also a video of how to do all of this. You don't have to be super left in the dark with how to operate this calculator. Please don't mess around with it. If the sub finds out you're messing around with it, then she's gonna take it. He's gonna take it, whoever it is, and you're not gonna get to do any of this. It's pretty fun. Okay, starting off with exercise 1. So, a sports writer wants to estimate the average number of wins from majority league baseball teams over the past 10 years. Major league, sorry, not majority. He uses results from 2016 as his sample. The number of wins for each of the 30 major league baseball teams in 2006 is listed in the table. So, we have this data set. He's calculated a sample for us. He's taken all of 2016, but he doesn't want to look at 2016. He knows about 2016. He wants to look for the last 10 years and maybe even make predictions about the next couple years, something that could get him a lot of money if he's right. It's called sports analysts. Yeah, cool. People actually get paid to do that. So we're going to use a calculator to find the average mean number of wins of the 30 teams in 2006. We're also going to use the calculator to find the standard deviation number of wins in the sample. And then we're going to find the number of teams who are more than one standard deviation above the mean. All right. Let's be very clear. The things we are finding are not mu and sigma. The things we are finding are x bar and s. Right? These are the ones that are known. These are the ones that are calculated, that our calculator will now calculate. These are not everybody for the next 10 years or the last 10 years or whatever. So we're going to find x bar and s. All right, so as you saw in our calculator, we found that the average number of wins, the x bar, was 80.9. And the standard deviation was 10.48. And our calculator basically did that for us. So now we have to answer the number of teams who were more than one standard deviation above the mean. Now we have those data points, or that data, we have what is the mean and what is one standard deviation above that mean. Well, the mean, as we just saw, was 80.9. One standard deviation of 10.48 above that would be, 80.9 plus 10.48, 91.38. Now, 0.38 of a win, does that make a lot of sense? We don't know. Probably not. But how many teams were above that? We're going to go back to our data set now. I'm going to kind of X-nay all the 80 things because we know anything below 90. Someone may have already put this. Anyway. Okay. It looks like over here, okay, so we've got some wins up here, right? We've got 90s above, it's got to be above 90.38. So we're looking at anything 92 or above I'll cut out all the 90s, but I also got to cut out this 91. It looks like 1, 2, 3, 4, 5. 5 teams. Only 5 teams were above 1 standard deviation. This is an incredibly accurate sample. This is normal, right? This is our normal sample. It is one of those ones that might have a normal curve pretty close to this, right? A very, very steep line. I'm going to draw it a little more even. Now, we don't actually know it's normal yet. We haven't tested that the other side also has less than standard deviation, but, you know, it could be that a lot of people are within this 1 standard deviation mark. So, very nice. Alrighty, let's go on to number 2. Let's start identifying some pieces of this. Kind of, now we know we have populations, parameters, samples, and interests. So let's look at that. A local electrician union desires to find the annual income of its 800 union members. The union surveys 120 of its members and asks questions about income. Identify the following in the information: the population, the parameters, the samples, and the statistic of interest. Okay, so population. Who would be the population? We're not saying all union members everywhere, right? We're going to say the 800 in this union. Do you always get a population number? No. Take, for example, you know, the drug argument again. We don't know how many people are going to be taking this drug. We just don't know, right? We don't know if it's going to be super popular or nobody's going to want it. So usually we would just be a little more ambiguous. We'd say the union members. But here we actually know that number. We know that there's only 800. So there's 800 union members in this population. Does that mean we're going to ask all 800? Absolutely not. The sample that they actually asked was 120. The 120 surveyed. That was the sample. So of those 800, they only asked 120. All right, what were the parameters? What are they actually after? They were after the annual income. They asked about the income. So they asked, I'm sorry, that's the statistic of interest. Let's start with stats of interest, because usually that helps us find our parameter. The stat of interest in English would be the income and the average income. Well, what's an average? An average is a mu. And so our parameters would be mu and sigma. You see how that works? So you look at kind of what in the real world are they trying to find. Oh, that's going to tell you your parameters. And no, they're not always going to be mu and sigma. Okay? That's it, though. We've identified all 4 things. Let's go to the next one. In a recent study of 320 students from Harvard, the average score on a standardized test was 95%. The students conducted the survey using this data to claim that the standardized test was a waste of time. Identify the population, parameters, sample, and statistic of interest. If the average was 95%, could very well be the case it was a waste of time. But does that really mean, is that really accurate, or is it just because you sampled those 320? That's the question. We're not going to answer that question. Instead, we're just going to identify the pieces. So, population versus sample. This one's tricky. The sample was the 320 students that got surveyed. The population, all Harvard students. So, sample, itty bitty little piece of Harvard that they actually took the score, or took the standardized test. Everyone at Harvard is the population. Absolutely everybody who has to or maybe will ever take this test. Okay. The statistic of interest. It may say, is it a waste of time, right? That is a good question, but that's not really a statistic. The statistic is the average on the test. The percent on the test or the average on the test. Okay. Therefore, our parameter, we actually kind of have a choice here. If you go for the average, I would say you could use U and sigma, right? With mu comes sigma. You could also say the percent. The percent of people who are going to be claiming this test is too easy, right? You could argue both ways on this one. I might just go with mu and sigma, though, because it's an average on a test. We'll be talking about tests a lot, and then you get your parameters, mu and sigma out of that. Remember, x bar and s are not parameters. We know those, These ones are the ones we're trying to make claims about. Either a percent of people wanting somebody to vote for, or liking the Amazon Echo, a percent of things like that, or an average of some score or some like average income, or whether you like it or not. Not like it. Any like yes or no question, probably a percent. Anything that's an actual like question, mu and sigma. Okay. All right, so let's on this last one just try out one more of those entering the datas, and then you can make statements yourself, whether you want to think what the populations and stuff are. But let's just practice with the calculator one more time. We have the website Rate My Phone conducts reviews of smartphones. One aspect of the phone that is tested is battery life. The minutes of battery life of the newest 25 phones is recorded in the table below. Use the statistics calculator to find the mean, standard deviation, and sample size. So not your cell phone. Your cell phone won't do it right, okay? Even if it's on Desmos. Plus, you can't use it on tests. So try now with your calculator. I'm going to recommend that you pause the video, and then go back in and see what you get. All right, so from our calculator, we saw that the X bar, the average, was 420. The standard deviation, the 115.83, and the sample size N 25. Again, we already knew that one, right? We've done what it's asked, but let's talk about it for just a minute. Does this mean we can actually make a good claim about whether this is accurate or not? Like, is this website really conducting enough reviews? 25 phones? Not bad, but is it just one of each phone? Right? Because there are 25 different phones out there. Definitely 25 different types of phones. Are they doing one of each? Should they maybe do 5 of each? Should they do 15 of each? Should they do 100 of each? A lot of people use cell phones now. A lot of people depend on their smartphones now. So if they're really worried about, or they're really wondering whether they're credible or not, is 25 big enough? That's really the big question, right? 420 sounds like an awesome average hour life, right? That's, I believe, 7 hours? Yeah, 7 hours. Sounds pretty accurate, but it could be wrong. I hear people complain about their battery life all the time, right? It could be wrong. And 115, that's a huge standard deviation. That means in between. So if I take 420 and minus 115-ish, that's already down to 300. That's already down to 6 hours. So we're looking at a span of 5 to 7 hours. Maybe 25 wasn't enough. Maybe 25 wasn't enough to say this works. Or maybe it really just is the case that it really depends on the phone, right? So there's still a lot of questions about this study. How to handle that and what we can do with that kind of information is going to come up in the next couple chapters. So, I'm sorry, next couple sections. You have plenty of homework time now. Go ahead and work on that. If you have any questions, ask the sub or shoot me an email. See you in 7.5.